Today we're diving into the fascinating world of radioactive decay. Have you ever wondered how some elements can change into others all by themselves? That's the magic of radioactive decay, a natural process happening all around us even though we can't see it. In this video we'll explore what radioactive decay is, why it happens, and how it impacts our world. From the basics of unstable atoms to the real-life uses and dangers of radioactivity, we'll break it all down step by step. Let's start by understanding what makes an atom radioactive in the first place. Understand radioactive decay, we need to know a bit about atoms. Atoms are the tiny building blocks of matter made up of a nucleus containing protons and neutrons surrounded by electrons. Most atoms are stable, but some have too many or too few neutrons, making them unstable. These unstable atoms are called radioactive isotopes. Their instability is what leads to radioactive decay, as the atom seeks a more stable form. Let's take a closer look at what makes an atom unstable and how this instability sets the stage for decay. Radioactivity is the process by which unstable atoms lose energy by emitting radiation. This radiation can come in different forms, such as particles or electromagnetic waves. When an atom is radioactive, it means its nucleus is unstable and will eventually change to become more stable. This change is what we call radioactive decay. The process is spontaneous and cannot be controlled or predicted for a single atom, but it follows certain patterns when looking at large numbers of atoms. There are several types of radioactive decay, each involving different changes in the nucleus. The three most common types are alpha decay, beta decay, and gamma decay. In alpha decay, the atom emits an alpha particle, which is made of two protons and two neutrons. Beta decay involves the transformation of a neutron into a proton or vice versa, releasing a beta particle. Gamma decay, on the other hand, releases energy in the form of gamma rays without changing the number of protons or neutrons. Each type of decay changes the atom in a unique way. Start with alpha decay. In this process, an unstable atom releases an alpha particle, which consists of two protons and two neutrons. This emission reduces the atomic number by 2 and the mass number by 4, turning the atom into a different element. For example, when uranium-238 undergoes alpha decay, it becomes thorium-234. Alpha particles are relatively heavy and don't travel far, but they can cause significant damage if they enter the body. This type of decay is common in heavy elements. Next, let's look at beta decay. In beta decay, a neutron in the nucleus changes into a proton, or a proton changes into a neutron, releasing a beta particle in the process. This beta particle is either an electron or a positron depending on the type of beta decay. The atomic number changes by 1, but the mass number stays the same. Beta decay is important in many natural and artificial processes, including the decay of carbon-14, which is used in radiocarbon dating. Gamma decay is a bit different from alpha and beta decay. Instead of changing the number of protons or neutrons, gamma decay releases excess energy from the nucleus in the form of gamma rays. These rays are a type of electromagnetic radiation, similar to X-rays but much more powerful. Gamma decay often follows alpha or beta decay, as the nucleus settles into a more stable energy state. Gamma rays can penetrate deeply into materials, making them both useful and potentially dangerous. Key concept in radioactive decay is half-life. The half-life of a radioactive substance is the time it takes for half of the atoms in a sample to decay. This period can range from fractions of a second to billions of years, depending on the isotope. Half-life helps scientists predict how long a radioactive material will remain active and is crucial in fields like archaeology, medicine, and nuclear energy. Understanding half-life allows us to measure and use radioactive materials safely and effectively. Sometimes radioactive decay doesn't stop with just one transformation. Instead, the product of one decay can itself be radioactive, leading to a series of decays known as a decay chain. For example, uranium-238 decays through a series of steps before finally becoming stable lead-206. Each step in the chain involves a different type of decay, and the process continues until a stable isotope is formed. Decay chains are important in understanding how radioactive elements change over time in nature. One of the most interesting things about radioactive decay is that it's completely spontaneous. We can't predict exactly when a particular atom will decay, but we can predict the behavior of a large group of atoms. This randomness is a fundamental part of quantum mechanics, the science that explains how tiny particles behave. The spontaneous nature of decay is why radioactive materials are used in random number generators and scientific experiments that require unpredictability. Radioactivity was first discovered in 1896 by Henry Becquerel, who noticed that uranium salts emitted rays that could expose photographic plates. Soon after, Marie and Pierre Curie expanded on this discovery, isolating new radioactive elements like polonium and radium. Their pioneering work laid the foundation for our understanding of radioactive decay and opened up new fields in science and medicine. The discovery of radioactivity changed the way we see the world at the atomic level. Marie Curie is one of the most famous scientists associated with radioactivity. She was the first person to win 2 Nobel Prizes, one in physics and one in chemistry, for her groundbreaking work on radioactive elements. Curie's research not only advanced our understanding of radioactive decay, but also led to practical applications in medicine, such as cancer treatment. Her dedication and discoveries continue to inspire scientists around the world. To study radioactive decay, scientists use special instruments to measure radioactivity. The most common tool is the Geiger counter, which detects radiation by counting the particles emitted by decaying atoms. Other devices, like scintillation counters and dosimeters, help measure different types of radiation and their intensity. Accurate measurement is essential for ensuring safety in environments where radioactive materials are present, such as hospitals, research labs, and nuclear power plants. Radioactivity is measured in specific units. The Becquerel BQ is the standard unit, representing 1 decay per second. Another common unit is the Curie CI, which is much larger and used for bigger samples. When measuring the effect of radiation on living tissue, we use units like the Sievert SV and the REM. These units help scientists and doctors assess exposure and ensure that people working with radioactive materials stay safe. Radioactivity isn't just found in laboratories or nuclear reactors, it's all around us in nature. Many rocks and minerals contain small amounts of radioactive elements, and even the air we breathe contains radioactive gases like radon. Cosmic rays from space also contribute to natural background radiation. Understanding these natural sources helps us put the risks of artificial radioactivity into perspective and reminds us that radioactivity is a natural part of our environment. In addition to natural sources, humans have created artificial sources of radioactivity. Nuclear power plants, medical imaging devices, and industrial equipment all use radioactive materials for various purposes. While these technologies bring many benefits, they also require careful handling and regulation to prevent accidents and limit exposure. The balance between the advantages and risks of artificial radioactivity is an important topic in science and public policy. Radioactive decay has many important uses in medicine. Radioisotopes are used in imaging techniques like PET scans, which help doctors see inside the body and diagnose diseases. Radioactive materials are also used in cancer treatment, where targeted radiation destroys cancer cells while sparing healthy tissue. These medical applications have saved countless lives and continue to advance with new research and technology. Archaeologists use radioactive decay to date ancient artifacts and fossils. The most famous method is radiocarbon dating, which measures the decay of carbon-14 in organic materials. By comparing the amount of carbon-14 remaining in a sample to what would be expected in a living organism, scientists can estimate how long ago the organism died. This technique has revolutionized our understanding of history and prehistory. Radioactive materials are also used in industry for a variety of purposes. They help inspect welds and materials for flaws, measure the thickness of products, and even power remote devices like space probes. The ability to harness radioactive decay for these applications has improved safety, efficiency, and innovation in many fields. However, strict regulations are necessary to ensure that workers and the environment are protected from potential hazards. Nuclear power plants use the energy released by radioactive decay to generate electricity. In these plants, uranium atoms undergo fission, a special type of decay that splits the nucleus and releases a huge amount of energy. This energy heats water to produce steam, which drives turbines and generates power. Nuclear energy is a major source of electricity in many countries, offering a low-carbon alternative to fossil fuels. One of the biggest challenges of using radioactive materials is dealing with nuclear waste. The byproducts of nuclear reactions remain radioactive for thousands of years and must be stored safely to prevent environmental contamination. Scientists are developing new methods to manage and reduce nuclear waste, including recycling and advanced storage solutions. Ensuring the safe handling of radioactive waste is essential for the future of nuclear energy. Protecting people from the harmful effects of radiation is a top priority wherever radioactive materials are used. Safety measures include shielding, limiting exposure time, and maintaining distance from sources. Personal protective equipment and monitoring devices help ensure that workers stay within safe limits. Public education and strict regulations are also important for preventing accidents and minimizing risks. Exposure to high levels of radiation can cause serious health problems, including radiation sickness, cancer, and genetic mutations. The effects depend on the type, amount, and duration of exposure. While small amounts of natural background radiation are generally harmless, accidents or improper handling of radioactive materials can be dangerous. Understanding these risks helps us use radioactive materials responsibly and safely. Throughout history, there have been several major nuclear accidents, such as the Chernobyl disaster in 1986 and the Fukushima accident in 2011. These events released large amounts of radioactive material into the environment, causing health and environmental problems. They highlighted the importance of strict safety measures and emergency preparedness in the nuclear industry. Learning from these accidents has led to improved safety standards worldwide. Radioactive decay isn't limited to Earth, it also plays a role in space. Many spacecraft use radioisotope thermoelectric generators, RTGs, powered by the decay of plutonium-238 to generate electricity. This technology allows probes to operate far from the sun, where solar power isn't practical. Radioactive decay also helps scientists study the age and composition of planets and meteorites, expanding our understanding of the universe. Radioactive decay can have both positive and negative impacts on the environment. While natural background radiation is usually harmless, accidents or improper disposal of radioactive waste can contaminate soil, water, and air. On the positive side, radioisotopes are used to track pollution and study environmental processes. Balancing the benefits and risks of radioactivity is crucial for protecting our planet. Radioactive decay has played a role in the evolution of life on Earth. Natural radiation from rocks and cosmic rays can cause mutations in DNA, some of which lead to beneficial changes and drive evolution. While high doses are harmful, low levels of radiation have contributed to the diversity of life over millions of years. This connection between radioactivity and evolution is a fascinating area of scientific research. Besides carbon dating, other radioactive dating methods use isotopes like potassium-40 and uranium-238 to date rocks and minerals. These techniques help geologists determine the age of the Earth and understand geological processes. By measuring the ratios of parent and daughter isotopes, scientists can calculate how long a rock has been forming. Radioactive dating is a powerful tool for unraveling Earth's history. Radioactive tracers are used in science and industry to follow the movement of substances. By adding a small amount of a radioactive isotope to a system, scientists can track its path using detectors. This technique is used in medicine to study blood flow, in agriculture to monitor fertilizer uptake, and in environmental science to trace pollutants. Tracers provide valuable information without causing harm when used properly. Radioactive decay is used to improve food safety through a process called food irradiation. By exposing food to controlled amounts of radiation, harmful bacteria and pests are destroyed without making the food radioactive. This process extends shelf life and reduces the risk of foodborne illness. Food irradiation is approved in many countries and is an important tool for ensuring a safe food supply. Radioactive decay can even help authenticate works of art. By measuring the levels of certain isotopes in materials like canvas or pigments, experts can determine when a piece was created. This technique helps identify forgeries and confirm the age of valuable artworks. Science and art come together in this fascinating application of radioactive decay. You might be surprised to learn that radioactive decay affects our daily lives in many subtle ways. Smoke detectors, for example, use a small amount of americium-241, a radioactive isotope, to detect smoke particles. Some glow-in-the-dark watches and emergency exit signs also rely on radioactive materials. These everyday uses show how radioactivity can be harnessed safely for practical benefits. Deep inside the Earth, radioactive decay generates heat that drives geological processes like plate tectonics and volcanic activity. The decay of elements like uranium, thorium, and potassium releases energy that keeps the Earth's core hot. This heat is essential for maintaining the planet's magnetic field and supporting life by recycling nutrients through volcanic eruptions and earthquakes. Scientists use radioactive decay to estimate the age of the universe. By studying the ratios of radioactive isotopes in ancient stars and meteorites, astronomers can calculate how long these objects have existed. This information helps us understand the history and evolution of the cosmos, providing clues about the origins of stars, planets, and galaxies. Radioactive decay can cause mutations in living organisms by altering DNA. While most mutations are harmless or even beneficial, some can lead to diseases like cancer. Scientists study these effects to understand how radiation influences genetics and to develop better ways to protect people from harmful exposure. This research is important for medicine, agriculture, and environmental safety. Radioactive decay is a key part of how nuclear weapons work. The rapid release of energy from fission or fusion reactions creates massive explosions and releases dangerous radiation. The development and use of nuclear weapons have had profound effects on global politics and security. Understanding the science behind these weapons is crucial for efforts to prevent their spread and promote peace. Forensic scientists use radioactive decay to solve crimes and identify remains. Techniques like radiocarbon dating can determine the age of bones or other evidence, helping investigators piece together timelines. Radioactive tracers can also be used to track the movement of substances in criminal investigations. These scientific tools have become essential in modern forensic science. Radioactive isotopes are used in agriculture to improve crop yields and food safety. Tracers help scientists study how plants absorb nutrients, while irradiation can eliminate pests and diseases in crops. These techniques contribute to sustainable farming and help ensure a reliable food supply for growing populations. Radioactive tracers are used to study water movement and detect leaks in pipes and reservoirs. By following the path of a tracer, engineers can identify problems and ensure that water supplies remain safe and efficient. This application of radioactive decay helps protect public health and conserve valuable resources. Scientists use radioactive isotopes to study past climates and environmental changes. By analyzing ice cores, sediments, and tree rings, they can reconstruct temperature and atmospheric conditions over thousands of years. This information helps us understand how the climate has changed naturally and how human activities are affecting the planet today. Radioactive decay helps museums and historians authenticate and preserve ancient artifacts. By measuring isotopes in materials, experts can determine the age and origin of objects, ensuring that collections are genuine and well documented. This scientific approach adds a new layer of understanding to our cultural heritage. Study of radioactive decay continues to drive innovation in science and technology. New materials, medical treatments, and energy solutions are being developed thanks to our understanding of how atoms change over time. As research advances, we can expect even more exciting discoveries and applications in the future. With great power comes great responsibility. The use of radioactive materials raises important ethical questions about safety, environmental protection, and the potential for misuse. Scientists, policymakers, and the public must work together to ensure that radioactivity is used for the benefit of society while minimizing risks. Open dialogue and responsible decision-making are key to navigating these challenges. Future of radioactive decay research is bright. Scientists are exploring new ways to use radioactivity in medicine, energy, and environmental protection. Advances in technology are making it safer and more efficient to harness the power of radioactive decay. As we continue to learn, radioactivity will remain a vital part of science and society. We've covered a lot about radioactive decay, from the basics of unstable atoms to the many ways this process shapes our world. Radioactive decay is a natural phenomenon with far-reaching effects in science, medicine, industry, and the environment. By understanding how it works and using it responsibly, we can continue to benefit from its power while keeping people and the planet safe. Thanks for joining us on this journey through the world of radioactive decay.